Okay, so my name is Pablo Herrero. I'm a postdoc at the Hebrew University. And the title of my talk is a question, are neutrinos their own antiparticles? And before I dive into it, let me say a few words about how I would like to frame this talk. It's a fascinating project with many branches, subtopics. Each of them deserves their own talk. And what I want to do is give a sort of trailer. So since the name of my experiment is Next, I created Nextflix. There we go. And just to show these snapshots here and there during the talk, also I'll show this slide in the end, to remind you that all of these, they deserve a documentary of their own. And so with that, let's start. The first topic will be anticosmos. This has to do with the title of the talk. I said, are neutrinos their own antiparticles? So what are antiparticles? We all know that matter is formed by protons, neutrons, electrons. But maybe what you didn't know is that these particles have partners, which are called antiparticles, and they are the mirror image. And this may connect to Giacomo's talk. Actually, they also define themselves in this mirror. And the key is that the particles and antiparticles have the same properties, for example, the mass, but for a notable exception, which is the charge. So if you have an electron, the antiparticle will have a positive charge. And if you notice, there is a small bar over the antiparticle there. That's how we denote it. So why is this important? The idea is that in the Big Bang, we have creation of particles and antiparticles in the same amount. And this is the only operation that is known in physics to create matter. And so this is what basically brought the universe here. But as I said, it's a symmetrical process. You have as many particles as antiparticles. That means that you would also need to have an anti-universe. And here comes the first problem. We don't see an anti-universe nowadays. So what happened to it? And the second problem comes because this process can happen backwards. So when particles and antiparticles meet, they annihilate and they disappear. And as I mentioned, if we had as many of one as the other, and we think about the early universe when everything was very close together, then this could have happened and all of it would have disappeared. But we are here, so we are the living proof that this didn't happen. And we should understand why this is not the case. And we think the solution to this puzzle could be a sort of double agent or a joker in a deck of cards, if you want to think about it. This would be, let's say, a sneaky spy that could go undercover and pass as matter or antimatter, and then jump from one side to the other of the balance and create this tilt that we need. So what could this double agent be? We think it's a very small particle that is called neutrino. It's represented by this symbol, this Greek letter nu. This is the antineutrino with the bar. And as you see, we think that they could be a double agent if they behave like this, if they are the two sides of the same coin. But this is a property that has not been proved yet. And actually, this is an important question by itself. That would be, if we could prove it, that would be a breakthrough by itself. So that's what defines the title of the talk. Are neutrinos their own antiparticles? Are they two sides of the same coin? And in order to answer this question, there is one single way to do that. And in order to explain it, you have to bear with me for a second because I have to explain something related to radioactivity. It has to do with how we can get antineutrinos, how we can play with antineutrinos. So this is a periodic table, and if we think of a beta decay, for example, of potassium, what happens is that it gets transformed into another atom, so calcium, and in the process, you have an emission of an electron, which they used to call it beta decay because they didn't know it was an electron, but also an antineutrino, and this, as you know, is one of the main characters of this story. But we need the other character. We need the neutrino to see how they interact with each other. So for that, we need another kind of reaction, a bit more advanced, which is simply called a double beta. Double beta decays occur because some atoms, like noble gases, let's say xenon, are very stable by themselves. So they don't just bother decaying once, they do it twice. because then they fall into this column, which is a bit more stable. And as I said, it's a double beta, so you have the emission of 2 betas, 2 electrons, and also 2 antineutrinos. This is already an interesting reaction by itself, but it's not super, super interesting. The actually interesting reaction that will happen is only possible if neutrinos are their own antiparticles, and then the coin can start to flip. And if this happens, you can have the situation where a neutrino and antineutrino find each other and disappear. And this is a third type of reaction that has not been found yet, ever. And it's called neutrinoless double beta decay because there is no emission of neutrinos. And over there is how you abbreviate it, it's your new beta-beta. So with that, that's the answer of how you can prove that neutrinos are their own antiparticles. You just have to detect this reaction called neutrinoless double beta decay. But now, here's a question. How can you detect the lack of neutrinos? It seems a bit tricky. It's actually possible. What you do is you focus on the energy of the electrons that are being emitted. So if you look at the, let's say, boring case, at the not so interesting case where you do have neutrinos, then this energy, every time that you measure this reaction, goes up and down. It's not completely well defined. But instead, if you look at the interesting case, the energy is always maxing out because the electrons get all the energy. There is no neutrinos. So in principle, this should be straightforward to distinguish between the two of them. Problem comes when you look at the times that a single atom takes to decay. Do you want to take a guess how long that could be? Order of years, centuries? Huh? Okay, I'll tell you. It's 10 to the 27 years. So now, talk about emotion regulation now. This, I checked it out, and this it's called an octillion years. And for reference, the age of the universe is only 10 to the 10, which is 10 billion years. Okay? The trick is that you don't look to only one atom, you look at an octillion of them. But still, this is difficult. So with this, I can show you the adventure map. We've seen already the antimatter problem, how neutrinos can be their own antiparticles, how you can prove this with the neutrinoless double beta decay. And now let's talk about how, like real experiments, what people are trying to do to prove that this reaction can happen. Enter next. This experiment of which I'm part of. And this experiment takes place in the Spanish Pyrenees. Why it takes place here is actually interesting. You can ask me about it. And this is the acronym. I love it because it already contains another acronym. This is how we physicists are. This is a recent picture of the collaboration. That's me. And it's formed by institutions from all over the world, mainly the US, Spain, but also the UK, Germany, and of course, Israel. And so what the next experiment does is the only detector in the world that is capable of taking pictures of the double beta decay. And this is so because xenon has electroluminescent properties. So these two electrons, where they are ejected, they leave this sort of trace. They leave a light signal that we can actually reconstruct. You can think of it as a sort of foot trace, following an animal, let's say. These are actual pictures that you can get with NEXT. You can see that they have two blobs from the two electrons. But often the problem is that you have other signals that are similar, but they actually come from backgrounds. They come from other uninteresting events. And actually, this background is very, very high. It literally rains on the detector. And this means that if you want to think about how this challenge is, it's not only looking for a needle in a hay. It's more like looking for a single grain of sand in a beach of 70 kilometers. But how can this be done? Let's say that there's been an idea. What if you could make this grain of sand shine? Enter my part of the experiment. I don't know why that moved. It's called BOLD, and it's named after barium light detection. So why barium? I didn't mention it yet, but barium, you've seen it all over in the slides, is the product of the decay of xenon. And moreover, it can be moved to one of the sides of the detector, and while this trace is formed, then the ion arrives, and you can have a sort of sensor there, and the sensor can produce some sort of light to detect the xenon. And what is important here is that barium it can only be produced inside this detector by the double beta decay. That means that if we had before a food truck, now we have the food truck with a certified tick there. And it cannot, so that means that this has to be the signal that we're looking for, it cannot be background. And what we propose to do to actually have this sensor working is to have a monolayer of organic molecules like this that are able to trap the ion and produce fluorescence. And actually the fluorescence changes for molecules with barium with respect to without barium. So this is what I'm trying to do in my postdoc. I'm investigating the details of how this happens and how it can be implemented in the next detector. And with that, I'll come to the last piece of the adventure map. And I'd like to thank you and take questions or comments.